This case study is based on a reasonably small tailings slump at Cadia mine in Australia. INSAR fans like myself love this case study because it really is a slam dunk for the technology. Signs were present long before the slump. Don't worry, for balance, I will also present a case study that is the polar opposite of this. Still a dam, but definitely not a slam dunk. In March 2018, a failure occurred on a TSF at Cadia mine in New South Wales, Australia. The spill was minor. Not only was there no loss of life or equipment, it was completely contained in a lower pond. INSAR was not being used at the site at the time, and cracks were seen for the very first time on the day of the slump. This is therefore a retrospective study, which doesn't ask whether displacement could be seen, but rather, what would reports have looked like had we been monitoring the site? We happen to have an analyst who was unfamiliar with the site or the event, who made some manual assessments and drew lines that circumscribed any displacement that he saw. And he looked at the data in strict chronological order and wasn't allowed to go back and change anything in hindsight. And then as a follow-up, we gave the data to our automated processing approach and did nothing different or special with the data or the process. We processed it once and took the answer without iteration. So that too is in its own way a blind test. This case study is as much about comparing those two approaches as it is about looking at the results in isolation. Here is the pond. You can see I've marked the failure area. I'm going to start 144 days before failure, even though displacement was actually visible before that, around 240 days before failure. The yellow line on the left side of the embankment is one of the manually drawn contours. This represents potential displacement. So at this stage, the analyst wasn't certain that this was real. It's often a tough call to do that because what you really want is to be able to see the displacement grow over time to rule out other potential causes. But you also want to alert users as soon as you're sure. So potential contours are a nice compromise. Overlaid is a red shaded heat map of displacement, which represents results from the automated approach. Straight away we can see that the automated approach sees much wider scale displacement. The noise here is very low, and so in this case it's really able to find displacement which is just not visible to the naked eye. When the automated approach is really statistically sure that this is not noise, a black contour is drawn. This isn't about the magnitude of the displacement, but how well the displacement sticks out above the noise floor. For interest, these signal to noise or SNR contours are drawn at 4 standard deviations above the noise, and that's equivalent to around a 1 in 15,000 probability that the result is due to the chance alignment of noise. So you can see that the machine and a human agree somewhat. The machine is more sure of itself though in that area, hence the black contour. The machine also sees statistically significant displacement in the failure area, which the human completely misses, a full 5 months before the event. 121 days out, and the machine and the human have better agreement. The human now has the benefit of precedence and is now sure of himself. Green contours represent 0 to 2.8 centimeters of displacement. They both see displacement on that northwest side and near the failure area. About 3 months out, and there is an increase. The human analyst with that black box machine learning algorithm called a brain is now confident enough to outline more displacement than the machine, and has decided that this really is just one larger feature. And now 72 days out, and for whatever reason, the data quietens down. The human decides there's still enough evidence to mark confirmed displacement, similar to the previous. That's the green contour. Note that the human is at liberty to look back as far as they like at any interferogram of any length, as long as it's in the past. The machine learning approach, on the other hand, is based on interferograms formed using the current image and the previous 5. So here the machine approach has indicated displacement, but none of it above the signal to noise threshold. 2 months out, and for whatever reason there again is less displacement. The data here seems lower quality, perhaps influenced by a weather event. The machine approach picks out a tiny area of displacement west of the failure area. 36 days to go now, and there is a sudden increase in displacement, and the tiny area from the machine approach has increased in size. And there is a machine-drawn contour at the failure site. Note the bulge that the human draws in the green contour right of the failure area too. The bulge stretches down the embankment wall. And now 24 days to go, there is more displacement right in the failure area, and the human-drawn contour stretches down further on the embankment. 12 days to go, and that signal is clearly well above the noise for both human and machine. In summary, displacement, when measured using snapshot style or rapid reports, is clear 8 months prior on the embankment. 3 months prior, there is displacement at the failure site. 1 month prior, evidence for some kind of issue is much stronger. The way many increasingly choose to consume these results are to let this kind of report inform them when to go and look at the time series for more detailed analyses. And here we can see a time series over the failure area, and this considers a much larger data set going back 3 years, and therefore has much lower noise. Because of that low noise, the acceleration towards failure is much more obvious in the time series, and there is a sharp downturn at the right hand end which occurs around December, 3 months prior to failure.